Okay, can we see that okay online?
Very clear.
Brilliant. Okay, so what I'd like to talk about. Okay, so what I'd like to talk about today is something that I think concerns us all, and it's of particular relevance to SEGH, and it's because it's all about our chemical, geochemical, and biological impact and footprint on our planet. And so the title of my talk today is the Anthropocene, are we in a new geological epoch? So as I've been kind of introduced, I'm Professor A.Cundy. I'm based at the University of Southampton. I'm director of the GAU Radioanalytical Laboratories, and I'm also a member of the Anthropocene Working Group. So we've been working quite hard recently to look at whether the Anthropocene can actually be designated as a new geological epoch. So in terms of my presentation content today, hopefully I can advance the slides. Do bear with me a second. So Oliver, I don't know if it's possible for you to advance my slides or whether it's just something, because I don't seem to be able to do that from the from my screen. Shall I come out of share and go back in again?
Yeah, if we try again.
Right, let's try that. If not, I'll go back to non-screen view and see if we can do that.
Can you use the icons in the bottom left to go between?
Yeah, I'll do that. I'll do next. Perfect. Okay. Can you see the next slide now?
Yeah, we can see that.
Excellent. Perfect. Okay, so sorry about a slight delay. So my presentation today is going to be all about the Anthropocene. And I suppose it's relevant to SEGH. You know, are we living on a human-dominated planet? And can we actually see that in the Earth's accumulating geological record? And I'm going to look also at geochemical fingerprints, and particularly one of the suggested primary markers for the new Anthropocene epoch, radioactivity, radionuclides as potential global markers of something we call a great acceleration, and also the mid-20th century. And then I'm going to talk a little bit about the geological record, the recent geological record, and particularly how our impact on that has been distributed, preserved, and how easily we can measure it. And also I'll talk about the temporal resolution of the geological record in terms of discriminating our impact on the environment. And source fingerprinting. I'll give some examples from our candidate, what are termed GSSP sites. And I'll talk about that in a bit more detail in a little while. And then I'll make some conclusions and wider implications. And I think link back to some of my early work that was presented to SEGH and how that links. Okay, so we're talking today about the geological Anthropocene and the work of the Anthropocene Working Group as an introduction. So the term Anthropocene was originally coined by a Nobel laureate, Paul Crutzen, in the year 2000. And Paul Crutzen was at a meeting which was reviewing the first decade of research in the International Biosphere Program, or the IGBP, and there's a very long discussion going on about climate variability in the Holocene, our most recent geological epoch. And Paul Crutzen stood up and said, well, actually, why are we arguing about this? We're no longer in the Holocene, we're actually in the Anthropocene. And this was really one of the first times this term had been used, and it was used to describe, if you like, a new phase of the planet's geological history, where humans have become the dominant agent in terms of global biogeochemical cycles and ocean and atmospheric composition on the planet. So this crystallized really this comment from Paul Crutzen, a growing realization in the Earth system science community that human activities were fundamentally changing the Earth system. And actually, importantly, from a geological point of view, these changes will be long lasting and detectable far into the future. So the quote from the Anthropocene Working Group website is that many of these changes will persist for millennia or longer and are altering the trajectory of the Earth's system, some with permanent effect. They are being reflected in a distinctive body of geological strata, geological formations now accumulating with the potential to be preserved into the far future. So what changes are we talking about? Well, certainly if we think about atmospheric composition, it's very clear that human activity has dramatically influence the composition of the atmosphere. So if you look at two of the common greenhouse gases, CO2 and methane, I don't know if you see my cursor, but that's over on the right hand of the screen there. We can see basically the classic hockey stick shape profile of CO2 and methane in the atmosphere, with this sharp increase in the past few hundred years. But if we go further down through those diagrams and we look at the amount of land area under pasture and cropland and also urban land area, again, we can see this really dramatic increase in recent times of our modification of the physical environment and our lifestyles. And a lot of this is related to globalization. And so the Geological Society of London, the Stratigraphy Commission, took an interest in this and suggested there was a case for formally incorporating the term Anthropocene into the geological timescale. And so the Anthropocene Working Group were commissioned by the International Commission on Stratigraphy to examine the status, what's termed the hierarchical level, the geological importance, and the definition of the Anthropocene as a potential new formal division of the geological timescale. So this is arguing that potentially we've left the Holocene behind, the natural variability, and we're now in an anthropogenically modified global system, which we can detect in the geological record. So when we're talking about geological units, chronostratigraphic units, such as the Cretaceous, the Cambrian, etc., ideally a chronostratigraphic unit is exemplified and its lower boundary defined at a single locality, and that single locality is a physical location on the Earth's surface, and that's termed the global boundary stratotype section and point. That's a bit of a mouthful, so understandably, that's abbreviated to GSSP. And that's typically in marine deposits, marine strata for those deposits prior to the Holocene. Now, the Holocene is quite unusual in that it's defined by ice core records, okay? But traditionally, geological sections have been described in marine strata, and that relates to the often excellent fossil preservation within those marine strata. So here's an example of two of the ratified GSSPs. The one on the left there is for the Ediacaran period. So this is the part of the Precambrian, and this is in South Australia, okay, near Adelaide, in the Ediacaran Hills. And so this what you can see on that slide is actually what's termed the golden spike. So this is the point, a theoretical golden spike, in this case a small gold plaque, is hammered into the rock sequence to mark the base of the Ediacaran period. So here, this is the key type site section that geologists from all over the world can visit and actually compare their results against. There's also my arm there on the right hand side, which is pointing to a golden spike at the GSSP of the Piacenzian stage in the Pliocene. This is in southern Sicily. And I think I've included that really to show that we don't need to see a physical change in the rocks to actually designate a boundary. In this case, it all looks like pretty much marl or chalk, but that particular nail that's been hammered in, that's marked by pointed to by my fingernail actually, is marked by a biostratigraphic change, a change in the organisms which mark the end of one geological phase and the entering of another geological phase. So that's the, if you like, that's the tipping point from one phase into another. And this is what the Anthropocene Working Group is looking at for the Anthropocene, for a number of candidate sites around the world, drawing on very different geological materials. And the Anthropocene Working Group is examining whether these sites show a material fingerprint of the Anthropocene. So obviously a number of the audience are looking at environmental geochemistry and health. Here, this is very much focusing on whether some of the changes that we're observing in the environment that might be having health implications in terms of changing geochemical systems, can we actually see that recorded in the geological record? Now, those of you that have worked on sediment sequences like myself will know that we can use sediment sequences to reconstruct recent geochemical change from lake settings and other systems. The key question here is, can we pick up a global human fingerprint, and can we detect that in a range of different geological and geographical deposits? So, bit of a busy slide this, but I'll talk you through it. These are the candidate sites where the Anthropocene Working Group is looking at different geological materials to see if they retain a fingerprint of human activity. And particularly, do we see a step change in human activity in the sediments? And is that at a consistent time within these geological sequences? So the group's looking at marine sediments. So for example, the Gotland Basin in the Baltic Sea, estuaries, so San Francisco Estuary in the USA and Beppu Bay in Japan, lake systems such as Searsville Lake in the USA, Crawford Lake in Canada, CLN1 Ma in China, reef sediments, so basically corals, growing corals in Flinders Reef in Australia and the Gulf of Mexico in the USA, ice core record from Antarctica. So here we're looking at whether our environmental fingerprint of human activities is detected even in some of the remotest locations on Earth. And also there's a stalactite record that's been examined at the Ernesto Cave in Italy, the Śnieżka peatland in Poland, so a peat deposit, and an urban soil, an anthropogenic soil at Karlsplatz in Austria. And so these records have got various time durations, but what we're seeing actually is we're seeing a lot of environmental change, kind of step changes in environmental impact within these environmental signature or anthropogenic signature within these deposits around about 1950, the middle of the 20th century. And so this is kind of the phase that's being examined, but there are others who argue that the Anthropocene started much earlier, and I'll come on to that in a little while. So some example of the sedimentary records and the geochemical changes recorded at these sites. So Crawford Lake is one of the candidate sites to potentially act as a global stratotype section and point for the Anthropocene. And this is a varved lake sequence. So you can see very clearly in that cross section of the sediment there, we've got these nice varves. There's a bit of deformation there caused by the freeze coring process that was used to collect this material. And on the right of the slide there, you can see the change over time of three potential markers of the Anthropocene. We've got plutonium, plutonium 239-240, particularly showing an increase just before 1950, and then declining from 1970 really onwards, with a peak in the mid 1960s. SCPs, these are spheroidal carbonaceous particles. So this is work by Neil Rose's group at University College London. And particularly here, this shows spheroidal carbonaceous particles are an indicator of coal burning. So high temperature coal burning, these are effectively fine particles that are very, very widely distributed in the atmosphere. And here we're seeing a really step change from about 1950 onwards. And we also see changes in nitrogen isotopes related to effectively land clearance and redevelopment and fertilizer application. So again, we seem to be seeing a less clear change actually at this site in 1950. So this is from work published recently in the Anthropocene Review by Francine McCarthy and colleagues from Brock University in Canada. So the Baltic Sea example, and here we've got a little bit more that I'm comfortable with in terms of geochemistry. And so here, this is a site from the Gotland Basin. So this is a sediment core, and we can see very clearly there's actually quite a clear physical change in the core at about 25 centimeter depth. Shown also as in the density profile of that core, so shown by the X-ray image there in the center of the slide. We've also got a mercury profile in particular there, showing an increase in mercury. All right, it's a little bit up and down, but there is an increase in mercury. Particularly, we're also seeing a gradual increase in total polycyclic aromatic hydrocarbons, but a sharper increase recorded in DDT and DDT breakdown products within that particular sediment core. And we also see other fingerprints, but this record is actually, if we look at the manganese to titanium ratio, we're actually detecting manganese spikes there, which are related to oceanographic inwash events. So fresher water coming into this anoxic basin and causing precipitation of manganese dioxide in the sediment record. So, and again, we're getting a change here from about 1950 onwards. And our corals, one of our coral sites, the West Flower Garden Banks in the Caribbean. This is a growing coral, and you can see on the right of the slide there, this is the cut coral surface. So the kind of almost horizontal lines there on the cut coral surface are actually growth bands. The subvertical lines are caused by the saw, which is actually used to cut this sample. And here we've got a very sharp increase in the carbon-14 signature here relating to nuclear weapons fallout. So we've got from about 1955 increase onwards to a peak around 1960. And we've also got a change here in the coral skeleton nitrogen isotope ratios here from about 1960 onwards, and that's, we think, related to nutrient inputs from the Mississippi River and other sites. So we're really seeing a mixed anthropogenic change recorded within these sediment and coral sequences. So one of the key questions is, if we are in an Anthropocene, so we've actually moved into a new geological epoch where we're actually dramatically fingerprinting or impacting global biogeochemical cycles, when did it begin? And so as a number of people online will know, you know, our human impact on the environment didn't begin in 1950. For those of us that are able to attend the conference in Athens, there is a very, very long mining history in the Athens area and in Greece more widely, through the use of the mining of silver and other precious metals, which really kind of drove the development of Athens as a major power in the Mediterranean, wider Mediterranean region. So we know that we've been exploiting our environment and contaminating our environment for a very long time. And so there's been an argument that, well, actually the Anthropocene actually began relatively early, and it began with early farming. And you can actually see a rise in atmospheric CO2 and methane levels at about 7,000 years ago, which has been argued to be the result of land clearance, and also about 5,000 years ago due to development of rice farming and livestock cultivation. However, those changes actually that we see in those atmospheric gases could be insulation driven. So they could be, you know, caused by changes effectively in orbital variations in the Earth's orbit around the sun. And those rises are small and gradual. And important phrase there, diachronous. Now, this is really important when we're considering marking geological periods or epochs, because what we ideally want is we want some kind of fingerprint that's global and that occurs at everywhere at the same time all over the Earth's surface. If we're going to mark that as a base of a new geological epoch, which we can correlate with globally. So we should be able to go to any site and say, we find this change in the geological record. We know that occurred at the same time wherever we look on the Earth's surface or in geological materials. So that is when the change is synchronous or isochronous. Diachronous means that the change occurred at different times in different places. So due to the development of farming and cultivation, that didn't occur at the same time all over the globe. So farming spread out as a technology. The Industrial Revolution is similar, actually, but also technologies such as the Bronze Age. So the Bronze Age started very early in the Mediterranean and the Middle East, and spread to, you know, my home area, the UK, much later. So that technology reached us a lot later. So if you look at the Bronze Age, that occurred at different times at different places. So what we want is an isochronous signature or synchronous that occurred globally at the same time. We also see early mining and smelting lead anomalies in 3000 BP and 2000 BP. Relating to development in mining activity. The argument there is, though, that the signature of those is regional rather than global, and they're also smaller than later changes that we see in global lead distribution relating to gasoline, use of leaded gasoline and burning of leaded gasoline. One suggestion that's been made for marking the Anthropocene is the arrival of Europeans in the so-called New World in 1492. And that resulted in the deaths of some 50 million indigenous peoples in the Americas effectively through invasion and through disease, and also resulting in forest regrowth. So abandonment of agricultural settlements and forest regrowth. That coincided with a small abrupt decrease in atmospheric CO2 called the Orbis spike, which has been argued that could be related to this forest regrowth phase. The problem is with the Orbis spike, it's not correlatable in most geological archives. And also there's a questionable linkage to an anthropogenic cause. It could be related to insulation changes. The argument by Crutzen in 2006 was that actually the Anthropocene may be defined to have started about 2 centuries ago, coinciding with James Watt's design of the steam engine, a highly improved steam engine in 1784, which was really a kickstarter for the Industrial Revolution and arguably globalization. However, if we look at the 1950s and particularly the mid-20th century, it's been argued that here we see a real stratigraphic turning point. And this is termed the great acceleration of human impact on the planet. So there are a range of proxies which show a great acceleration impact from about 1950 onwards. That's a dramatic, continuous, and roughly simultaneous surge in growth rate across a large range of measures of human activity from the mid-20th century. And this is one of the arguments why actually the Anthropocene, or more correctly termed the Capitalocene, after capitalism or globalization. So here we can see in terms of our cumulative anthropogenic aluminium and concrete production on the upper graph, we see a large increase in aluminium production, concrete production, but also plastics manufacturing use, which are becoming incorporated into the geological record from 1950 onwards. We also see from around about 1950 a big increase in spheroidal carbonaceous particles, which are global fingerprints of coal burning and industrialization effectively. So it's been argued that this is actually a point at which we left the bounds of the Holocene behind and moved into a new period where humans were the dominant force on the planet in terms of biogeochemical cycles, in terms of sediment transport, and also importantly in terms of atmospheric composition, ocean composition, and also the hydrological cycle. Now, one area that the Anthropocene Working Group have been focusing on, and that actually brings in the expertise of a number of people within this virtual room today, is looking at radionuclides and radioactivity as potential global markers, or if you like, basal markers of this great acceleration in the mid-20th century. So the argument here is, can we use radionuclides as an indicator of the base of the Anthropocene if it's decided that the Anthropocene commenced around about 1950? Well, if we look at a nuclear timeline, so this is modified from a paper by Colin Waters, who's currently chair of the Anthropocene Working Group. This shows, it's quite a complex diagram, but I'll talk you through it. On the y-axis, this shows the aggregate number of nuclear tests. And so along the x-axis, we've got a timeline, and the solid bars show effectively the number of atmospheric nuclear weapons tests, and also the transparent bars show the number of underground nuclear tests. The blue line shows the deposition density of plutonium. Plutonium-239, 240. So those two isotopes are measured together when you use alpha spectrometry. And effectively here, the plutonium has been produced and released by these nuclear detonations. So particularly from 1950 onwards, with the initiation of high-yield thermonuclear testing, H-bombs. And that began with the 10.4 megaton Ivy Mike test at Enuitak Atoll in the Pacific Ocean on November the 1st, 1952. And really that's the point at which nuclear fallout, which had been produced regionally previously, shifted from being a regional to effectively a global fingerprint of nuclear activities. So this, during these bomb detonations, nuclear materials, including plutonium, were injected into the stratosphere and globally distributed. Also carbon-14. So carbon-14 is what we term an activation product formed by neutron bombardment when there's a nuclear detonation. And so again, we can see very clearly here this increase, slightly offset from 1950. It's coming in at about the mid-1960s. This is atmospheric carbon-14 concentration, which has accumulated an excess amount of carbon-14, effectively due to nuclear weapons detonations. So you'll note here that actually the main peak of plutonium fallout was in about 1963, and that follows a major phase of nuclear testing, above ground nuclear testing, which took place immediately after a testing moratorium between 1959 and 1960, and just before a limited test ban treaty in 1963. So we've got this kind of pulsed input of plutonium to the stratosphere and then into the global environment. We also, of course, so as I say, shown graphically there, commencing in about 1952 as a global fallout signature. We also have radionuclides released, of course, from accidents at nuclear power facilities, such as the Chernobyl disaster in 1986 and the Fukushima Daiichi disaster in 2011. But also, we've released radionuclides to the marine system and the atmosphere due to licensed discharges from nuclear fuel reprocessing complexes like Sellafield in the UK and La Hague in France. So they've input significant amounts of radioactivity to the environment, but the total input from those sources have typically been less than 1% that from atmospheric weapons testing. So they're a regionally significant input, but they're not a global marker. And it's a global marker we're thinking of when we're thinking of marking the base of the Anthropocene. So what are the key fallout products forming a stratigraphic signature? It's not my intention today to give you a lesson in nuclear physics, but what I want to do is just give you a brief rundown of some of the fallout products released following a nuclear detonation. And that depends on the characteristics of the device detonated and the nature of the detonation. But we can generally group these products into three main types, depending on their mode of generation. Fission products, which are caused by the fission or the splitting of a uranium atom. So here we see uranium-235 splitting into barium-144 and krypton-89, which are fission products. Commonly, we see isotopes, detectable isotopes like cesium-137 and iodine-129. We also find actinides, and these are generated by the absorption of neutrons to produce heavier elements. So here we've got plutonium-241 and americium-241 and plutonium isotopes as well, various isotopes of plutonium. And the pathway here is shown for plutonium-239. And we have activation products we've seen before, such as carbon-14. Now, actually, these fallout products are widely used dating tools. They often provide a first go-to method that most environmental scientists use to get an idea of the age of modern sediments in a core. Plus, they're used as water mass tracers. So, for example, tritium has been used as a water mass tracer in hydrogeology and in ocean circulation studies, and that's released from nuclear activities. So, how these radionuclides are incorporated into the geological record depends on their chemistry and the characteristics of the environment in which they're deposited. So the more particle reactive radionuclides show a strong interaction with the sedimentary and biological materials that make up the Earth's stratigraphic record. So the bomb peak in carbon-14 in about 1963 to 64 can be detected in most carbon reservoirs with variable offset. So in some corals, it's delayed due to ocean circulation pathways. These include, though, peat deposits, soil, wood, coral, and bone. Plutonium isotopes readily associate with clays and organic particles in lake, marine, and other settings. And here you can characterize distinct fallout signatures, as shown here in the Crawford Lake core, McCarthy et al. We're seeing a maximum here in the early 1960s, and that correlates and corresponds to this maximum fallout of plutonium from above ground nuclear weapons testing that I showed in the earlier slide. So, but if we think about using these radionuclides to potentially mark the Anthropocene or detect the Anthropocene as a global marker, not all latitudes are equal and not all deposits are equal. So the maximum fallout from nuclear weapons testing occurred largely in the northern mid-latitudes as a result of atmospheric circulation patterns, but also the location of some of the bomb testing. So we see a peak in fallout, illustrated here by strontium-90, at round about between 30 and 60 degrees north. Also, different deposits accumulate different amounts of radioactivity. So if we look at some of the potential global stratotype site and point sites for the Anthropocene, Crawford Lake has accumulated maximum activity in becquerels per gram. So a becquerel is 1 atomic disintegration per second. It's a measurement of radioactivity rather than concentration. You can convert it to concentration or mass though, of 17.8. The West Flower Garden Banks, the coral deposit from the Caribbean has a maximum activity of about 0.3. The Palmer Ice Core from Antarctica, which is ice, of course, has a maximum activity of about 0.014. So some deposits are easier to detect radionuclides in than others. And while plutonium is typically immobile once it's deposited, for example, it can migrate in acidic peak profiles, adding anthropogenic plutonium to deeper layers deposited before the period of nuclear weapons testing. Also, the carbon-14 present in deep marine sediments, which represent some of the key materials preserved in the geological record, give you a mixed signal of atmospheric and ocean carbon pools. But interesting enough, from the point of view of marking our global fingerprint on the environment, the signal of plutonium and carbon-14 is effectively global and can be detected using standard counting techniques in sediment, soil, coral, and ice. And so here the example from the Palmer Ice Core showing the very low activities that can be detected. These used a count time of over 30 days per sample, but you can still detect the plutonium. And it also builds on a very large literature, very large published literature showing plutonium accumulation in a range of different environmental settings, with the first papers on this being published in the 1960s. Also, using plutonium, we can fingerprint the source of the fallout and also the plutonium input. So the isotope ratios of plutonium. So if we don't just look at plutonium-239 and plus 240, if we look at the ratio between plutonium-240 and plutonium-239, that's a real fingerprint of the source, because that ratio depends on the characteristics of the nuclear device, but it also depends on what we term the burn-up time of plutonium in the material. So nuclear reactors will also generate plutonium within their uranium fuel rods. They're burnt over a period of months, effectively. So the heavier isotope plutonium has got a plutonium-240 has got a longer time to build up. That's produced by neutron adsorption. Whereas on the effectively instantaneous detonations that we see from the above ground thermonuclear weapons testing, many of those are dominantly plutonium-239 in composition. So there's not been time for those heavier plutonium isotopes to grow in and build up. So the key point here, and it's illustrated very nicely by this sediment core. So this is a sediment core collected from a salt marsh setting from a site near to the UK Sellafield nuclear reprocessing facility. And we've got dating here from lead-210 dating and from other dating methods. So here we can see that in the 1950s, we've got a very low plutonium isotope ratio. And that increases over time to peak in around about the early 1980s at a ratio of about 0.22. And that's tracking the change of plutonium discharge from Sellafield. Effectively, in Sellafield's early history, it was used to produce plutonium. A lot of the work was about generating plutonium for nuclear weapons. So here, that was a very quick system to produce the plutonium, and also the manufacturing process wants as much plutonium-239 as possible. You can think of the plutonium as a bit more of a contaminant in the process. Over time, Sellafield shifted its operation to nuclear fuel reprocessing, civil nuclear fuel reprocessing. So here at the top of the graph, we've got a much different ratio, and that reflects higher amounts of plutonium-240 in the discharges relating to the reprocessing of nuclear fuel materials. So here we can fingerprint potentially to the level of an individual nuclear test, and also distinguish between nuclear fuel discharges, nuclear site discharges, and weapons fallout. So, and at our global potential GSSP sites for the Anthropocene, we see a really nice fingerprint of plutonium beginning in round about 1950, potentially marking the base of the Anthropocene. So bear in mind, it's not just the plutonium. You've got a whole series of markers of this great acceleration, which you find in the upper sediments here in the Baltic. But the argument is you can potentially use the plutonium as a basal marker for the Anthropocene, which is synchronous around the globe. So we see it in the Baltic Sea core, and we actually, interesting there, see a change in plutonium isotope ratio, potentially picking up here some of the early Pacific testing, and also in the shallower parts of the core, picking up a characteristic signal of plutonium 240-239 from Chernobyl. And we also see it in our coral records as well. And really all of the potential candidate sites for this GSSP marking the Anthropocene, apart from the stalactite site actually, show an indication that plutonium can be used as a broadly synchronous marker for the Anthropocene, for the beginning of the Anthropocene across the Earth's surface. So conclusions. Radionuclides have been argued to be strong candidates to define the base of this Anthropocene, this new geological epoch. They're mostly absent in nature. They've got long half-lives that provide a long-lasting signature, greater than 100,000 years for plutonium-239. They've got potential to form a relatively fixed and isochronous time-synchronous marker in geological deposits. They're commonly used dating tools. They're present in sufficient quantities to be readily detectable. And they provide a high resolution record at a range of these candidate sites covering corals, ice and sediments, and in a wide range of other geological archives in published data from the 1960s onwards. They record the onset of thermonuclear testing in 1952 and subsequent fallout changes, with potential for source discrimination using plutonium isotope ratios. And even when activities are very, very low, advances in techniques such as accelerator mass spectrometry mean that mass isotopic abundances and isotope ratios can be readily determined. So for plutonium, we can actually determine down to sub-femtogram, sub-10 to the minus 15 gram per gram concentrations in geological materials. And this is some work that we recently completed with the University of Lausanne in Switzerland, led by Josh Chaplin, former PhD student, looking at actually the remobilization of plutonium and other radionuclides from environmental stores that contain, natural environmental stores that contain, they've accumulated cellular discharge products. And here we're able to use diffusive thin film technologies, diffusive gel technologies to actually detect fluxes of plutonium, mass fluxes of plutonium in grams per hours per centimeter squared of less than 10 to the power minus 17 using accelerator mass spectrometry. And also there's been work showing really the fine fingerprinting of plutonium by looking at plutonium-244, not as an anthropogenic input, but as an indicator of past supernova events. And that's been a range of work performed on mid-ocean ridge deposits and other deposits where it's capable to detect 15 atoms of plutonium per centimeter squared per million years. So actually some really precise AMS techniques coming on stream now for actually determining these radionuclides. So by way of final conclusion, really, the Anthropocene Working Group voting continues. So, and there's a proposal to go forward later this year to the International Commission on Stratigraphy to whether or not we can actually mark the Anthropocene as a new geological epoch. And whether or not the Anthropocene is formally ratified, it may be decided that actually, no, we're still in the Quaternary. The work has really highlighted the widespread and consistent impact of humans on the recent geological record, and importantly for us in SEGH on the planet. So, quote from the Natural History Museum website is that the Earth is 4.5 billion years old and modern humans have been around for a mere 200,000 years. Yet in that time, we've fundamentally altered the physical, chemical and biological systems of the planet on which we and all other organisms depend. And I think it's important to note that I've focused a little bit on radionuclides and geochemical fingerprints. A lot of the work of the Anthropocene Working Group is actually looking at records of extinction events, recent extinction events in the recent geological record, particularly linking that to microfossil and other abundances, and also the presence of invasive species as well as an Anthropocene marker. So while the term Anthropocene itself is widely used across a range of disciplines with different meanings, actually, the formalization of a stratigraphic Anthropocene can positively contribute to cross-disciplinary debates and highlight our long-lasting impact on the planet. And from a personal point of view, so some of the very early work I presented at SEGH conferences was actually looking at geochemical records in Southampton water, very close to the University of Southampton. And the rather pixelated paper there, heavy metal and hydrocarbon pollution, was my first ever paper in 1994. So last century, frighteningly. And basically this was looking at the heavy metal and hydrocarbon fingerprints of human activity, including the discharges from the Fawley oil refinery in Southampton water on the local geochemical record. So here we can see a spike in copper inputs related to refinery processes so the copper was used as a sweetening agent in refinery processes and was discharged into the local marine environment. So a lot of this work and a lot of work that's been published over the years in e.g. Environmental Geochemistry and Health Journal has actually looked at heavy metal, organic and radionuclide fingerprints in peats, sediments, so inorganic sediments and other materials. And I suppose at that stage, I didn't actually realize I was working on the Anthropocene. But I think a lot of the work that's been carried out historically in SEGH and currently has real implications for our understanding of whether we've entered a new geological epoch. And particularly, I know that Neil Rose, who does a lot of work on spheroidal carbonaceous particles, and myself on the radionuclide signatures, would be very interested in actually working with colleagues in SEGH, particularly African colleagues actually in looking at sedimentary and other records of environmental change. There's a big gap in the Anthropocene sites that I showed earlier on. In terms of the African continent, I think, in order to show that we've got a really truly global Anthropocene, it's important that we look at all continents and, and work with scientists around the world to see if genuinely we can detect our fingerprint globally and genuinely we've entered a new geological epoch. Okay, I thank you for your attention. I think that was about 35 minutes, hopefully, and I'd welcome any questions. Thank you.
Yes, thank you so much, Andy, for this evidence and data-based presentation. The SEGH president is having some network issues. He's stuck in an airport somewhere, so the network might be an issue. Thank you so much, everyone, for joining us. Please, if we have questions for Andy, I'm sure we have quite a number of questions. You can raise your hand or you can put it in the chat box so that Andy can deal with questions.
I think Alec has got his hand there first. Yeah.
Yes, and then we have Keith, and then we have Gabriel from Gabriel there. Okay, so we'll take Alecos, and then
thank
Keith,
you.
And then
well, I've been following the Anthropocene because of IUGS. And as you know, Andy, there is a lot of questions. Where is it starting? Yeah. Now, regarding the mining, this is, well, let's say one way, and you have shown that the early mining and smelting of lead started in 3000 BP before present. Well, that is incorrect, because the mining in Lavrion with isotopic lead ratios, it goes back to 3500 BC. So it's 6500 before present. Now in Cyprus, so the copper mining goes back to the fourth millennium. So 4000 BC. So if we follow the mining activities, we can go back a long time before the present. Now, regarding the plutonium ratios that you have shown, this shows the recent sort of fingerprint. And I would not, I will call it the Atomicocene, where we have the atomic age. So let's coin a new name, Atomicocene. So it's really difficult to put a marker, in my opinion. We have to have a lot of sub-markers. And for example, since you are working with sediments, I mean, we can see the Anthropocene in the floodplain sediment sequences as well.
Yeah.
So there's a lot of work still to be done.
Yeah, exactly. And there's some very good points there, Alekos, and I fully take your point about the onset of mining activity. I think the dates I quoted weren't actually from my work, they're from other work that was looking at more remote sites in terms of a kind of fingerprint of when that mining activity had, you know, a broader regional signal. But I completely take your point about the idea of the early Anthropocene. There's been a lot of discussion on when the Anthropocene should start, and actually whether or not the Holocene is actually by definition sufficient to cover our human activity, because when the Holocene was set up, it was argued that actually, or was designated, it was also the age of humans. So I think there's been a lot of discussion on between the geological and the archaeological communities, and certainly the naming of the Anthropocene, because the name Anthropocene is out there in a number of different disciplines, and different disciplines are using it to have very different meanings. And I think it's been a really useful debate, actually. And I think one of the key things now really is the Anthropocene an epoch, or is it actually an event or an episode? And so by having it as an event, the argument could be that it's actually much longer in duration. One of the issues we've got, though, if we use an event to incorporate all of human activity on the planet's surface, is obviously the fossil record becomes more and more difficult the further you move back. But you know, there's no guarantee that this will be ratified at all. And I think, but it has led to some really interesting debate in earth system science and geology and archaeology, whether or not it's, and other disciplines, whether or not it's ratified.
I think one point is that to define it, for example, should we say when humans started to really have an influence and impact on the whole Earth, sort of thing. So, and the problem is this impact is different in different continents.
Yeah, exactly.
That is the problem.
Yeah, and it's having to evidence really that we've got a truly global record.
Mm-hmm.
Can I ask my question now?
I think you're next, Keith. Yeah, go ahead.
Great. Well, thanks, Andy, for a brilliant talk. I wondered whether any consideration was maybe given to, you know, man-made artifacts which are probably appearing in the, you know, the sedimentary record now.
Yeah.
Obviously, microplastics might be one possibility. My own candidate would be the aluminium ring pull cans, which you know, is obviously a metal that requires a lot of technology to extract from its ore. Was very valuable at one point, and now it's thrown away.
Yeah.
So maybe that's a possible marker of the kind of disposable culture,
disposable society. Yes, yeah. No, I fully agree, Keith. I think the idea of using technofossils, you know, obviously, so you've got a range of new materials, ceramics, alloys, and they're going to be really, and new minerals actually, and they're going to be really persistent in the geological record. So I think one of the arguments about, you know, it's thinking about what might be preserved long into the future. And I think this, you know, like I say, the aluminium ring pulls. I've also seen broiler chicken remains proposed, because the broiler chicken is a very different bone structure to wild chickens. And so, you know, if we think into the future, there might be this layer around the Earth which has got, you know, technofossils in it, aluminium ring pulls, concrete, and other materials, and also the chicken bones, etc. So, and I think that's one of the problems that's been faced, in that it's quite easy to think of the future in terms of what might be preserved, but actually what the Anthropocene Working Group needs to look at is what's there now, in terms of whether that's sufficient to actually designate the marking of a new geological epoch. So, you know, it's been a very complicated process, because it's you know, we're obviously living through the period at the moment, or the epoch, if there is one, and so, you know, it's predicting what might happen in the future.
Thank you so much, Andy, for that. Gabriel, can we have your question? Andy?
Okay. Thank you. Thank you, Andy, for this presentation. Well, I am also very interested in the fact that you concluded your presentation by recognizing the fact that there's a gap in part of the Southern Hemisphere data that has been collected in the past. So my question is, one, I saw a range of data you showed when you started your presentation about other locations where core sediment has been collected, and I think there is one of them which is Antarctica. I don't know if it's actually ice core or is also sediment that you did collected there. So I would like to know that. Then my second question will be on the issue of the date when to talk about the Anthropocene. I'm actually working on plastic in the deep sea, in the Mediterranean, and we have seen a lot of things, and in core samples that were collected, and the plutonium, as suggested by the first speaker, the person who has the question, I think this is a very important fingerprint to look at. But your presentation as well also touched the fact that humans have been in existence for the past 200,000 years. So if we look at the activity of migration and humans' activities before 1950 and removing the nuclear test, how do we compress this entire volume of years?
Yeah.
And then decide to choose the Anthropocene? It's just my curious question.
Yeah, no, very, very good questions. Thank you. So the Antarctic sample was an ice core collected by the British Antarctic Survey. So that's ice, not sediment. But I think the point I'd make about the Anthropocene is basically I think it's important to realize that we're looking at a range of indicators. So plutonium doesn't actually indicate a change to the Earth system, but there are lots of other indicators, like Keith mentioned, technofossils, but yourself on plastics, that show this global change to the system and to cycles of the system. And I think where to start is really a fundamental question. And I think there is a geological Anthropocene, or there may be a geological Anthropocene if it's ratified, that depends on having a isochronous boundary globally. And as Alakas has said, it's the point at which we go to we can detectably see a global human impact, but that does in no way downplays the importance of earlier change. And I think what we're seeing is a trajectory of change. So we're seeing change from the very early humans modifying their environment, and it's not to downplay the importance of that. But what we're really saying is at what point did we go from having a regional impact, lots of regional impacts, to having a truly global impact for a range of indicators, so things like invasive species, extinctions, etc. And it's really when we see this exercise, that's why it's been argued that a good point could be the Great Acceleration, because it's when we see a large scale change in a lot of environmental indicators, including atmospheric composition, but it's not to downplay the earlier importance of human activity, because as we know, we're looking at a very long-term geochemical record and a very long-term human influence record as well.
Yeah. Okay, thank you. But another important point is that please, the core, extracted both in the north and south for just for globalization's sake, data should be carried along, so that wide samples from the north will say different thing for geological data sake. The southern hemisphere too probably has to correlate to that.
Yeah, and I think that's a really important point, that for the Anthropocene to become accepted, basically, there's a need to show that deposits globally, so not just these candidate sites, deposits globally actually show this recent change. And I think there's a lot of published work, including in EGAH, on showing exactly this.
Thank you very much.
Thank you.
Okay.
thank you very much, Andy, for those explanations. Thank you all for sticking with us this time. I would like to ask Andy, because later people might have questions that come up that they might need to discuss with you. Do you mind giving out an email address, maybe in the chat?
That's absolutely fine. I'm very happy to answer any questions, and yeah, and I'm very, very happy to discuss, the Anthropocene in more detail. So what I will do is I'll just put my email address in the chat.
Good.
So if I can spell that right. There we go. Hopefully you can see that.
Oh, yeah.
I'd welcome discussion, and thanks also for the questions. I think there's some great questions there, so thank you.
Thank you so much. Anyone, no more questions, I presume, for Andy on this very interesting topic on how we are affecting the stratigraphic time scale. Professor Latuji has been in and out of this meeting. He's taking this meeting at an airport, so I bet that the Wi-Fi connection is not very good. But yes, so we can see his message there. He's thanking you for this presentation, and he thanks all of us for attending and speaking with us. Will reach out to us sooner than later on the next in the series of the fellows lectures. We hope that all of you will join us as well while we discuss another interesting topic. So thank you all so very much, and enjoy the rest of the day.
Thanks all for your attention. Great to see you all online. Thank you.
Thank you again, Andy. Thank you so much.
Thank you very much, everyone.
Thank you.
Good day.
Thank you very much.
Madrid.
Thank you.